Okay, so addressing the rest of the pump questions. When you're actually trying to decide what kind of pump to implement in a specific site, there are a few things you need to take into consideration. First, you need to figure out how much water is going to be used. If you're going to pump a bucket of water a day, building an expensive rocker pump doesn't really make sense, and a hand pump will do the trick. Whereas if you're trying to irrigate your entire field, then maybe a cement pump is a better alternative to the hand pump because you don't want to sit there pumping with your hand for hours and hours and hours. That being said, the other thing is that different pumps can pump different amounts of water and can pump over different pressure heads. So the cement pump is a diaphragm pump, and I think it can pump about 5 to 7 meters deep only. So it's not really used to pump water from a low water source like a borehole or something like that, because it just won't be able to do that. A little bit about how it works is you have...
Been used for like filtrations and sanitation kind of, or just carrying and moving water. Like, can you put a filter? Seems really rudimentary, but can you put a filter at the end of one of them, kind of like a valve, and then just collect its dirt?
I've seen people use pumps with filters on them, generally larger pore filters. But the problem with that is you normally have to replace the filter every so often, and you don't want it in an internal part of the pump because it gets tedious to replace it all the time. But I've seen people put like just cloth filters over the end to get rid of turbidity.
Great. So it's because a pump is pushing out a relatively high pressure and filters tend to work slowly, it's rare that you can just put a filter at the end. So typically, while it would be great to just have point of use water purification and cleaning, apart from like turbidity factors, it's hard to do that effectively.
All right. So those are, I think, the two biggest questions from last week's lab. Do you know if you have more questions about last week's lab? Cool. So a little bit about what we're going to do today works. We'll go into that later, but this is more about how to use the PV panel and some applications that come from that. We're going to learn how to hook it up to a battery because that's one of the most common uses, I think. And we're going to look at some of the design considerations you're going to have to take into account when you look at designing a solar system. And so that's sort of one half of the lab, and the other half is going to be working in the shop again, and you're going to learn more about fabrication techniques, but this time instead of working with wood, we're going to look at other materials like metal and PVC and sheet metal. Cool. So, where's my sheet? Okay, so when you're trying to get energy, when you're trying to get power from the sun, you basically have your sun, and then you have the surface of your Earth, and rays coming in. Do any of you know how much, best case, when the sun is shining, there's no clouds blocking the way, what the best case power you can get from the sun is in watts per meter squared? Yeah, it's about 1,000. Now at the beginning, at the first class we sat in, we tried calculating the average daily electrical consumption, or average electrical consumption per year for people living in the developing world. And based off of those numbers, we have, you can approximate that people in Nicaragua use about 1 kilowatt hours a day. And then people living in Haiti use about 0.1 kilowatt hours of electricity a day. So if we're looking at solar, we're looking to power all of these, the 1 kilowatt hour or 0.01 kilowatt hours that people are using in the developing world using this energy. How much surface area would we need to harness the power? So we can walk through it, right? And we get And then you know that a day has 24 hours. So you can multiply that out. Yeah, it's true. I'll get to that in a second. So you get about that much surface area where you need. So if you could ideally harness the power of the sun at this efficiency, or at this much power for 24 hours a day, for one day you would only need you would only need a collector that's 0.04 meters squared, which is pretty tiny, which seems like a really good idea. But there are a lot of there are a lot of reasons why this is not the right way of figuring out how much power you need. So like you said, for example, the sun does. How far down can you guys read it again? Is it about here?
A little lower. There.
There. Okay. So yeah. So let's brainstorm some of these ideas or some of these reasons. Yeah.
So supply and demand is not always exactly matched. So there's no storage. In our equations right now there's no storage yet. So we might need fluctuations from 0 to 1 kilowatt hours.
Okay.
During the day.
You get like max about 30% from the voltaics.
That efficiency goes down even more as the panels age, and also if it gets any scratches or anything on them.
Okay, so let's start looking at some of these and quantifying some of these constraints we have now. So we can't do this anymore. Let's still work with these numbers as ballparks because, I mean, we're only really concerned with order of magnitude estimations really for this. So efficiency of PV, in max you get about 30%, but I think that's sort of the laboratory, like cutting grade technology that is really expensive. With commercially available PV, it's somewhere between 8 and 18% is what you're going to get right now. Yeah, we're not going to look at that one yet. So this one, about how many hours do you think should we approximate the sun to be up a day?